Okay, let's begin our second lesson on sequences, and we're going to look at some especially interesting ones and see once if we can discern what limit these sequences go to. Here's the first one: the limit of sine of n over n as n goes to infinity. And I throw this one up here just to show you that just by thinking about some of these carefully, you can often get the answer. Sine of n over n, let's think about it. Sine of n, you know that the sine of any number is always going to be between 1 and -1. And so this thing up here is going to keep bouncing back and forth between various numbers between 1 and -1, whereas the bottom is going to keep getting bigger and bigger and bigger. So the ratio, as the bottom gets bigger and bigger and bigger, the ratio of this over this is going to keep bouncing closer and closer to 0, right? It's going to bounce around depending on whether this is positive or negative. But as the n gets bigger and bigger, this little interval around 0 is going to get smaller and smaller, and you're going to just converge to 0. You see why? Given any interval around 0, eventually everything will be inside there. So that limit is equal to 0. Okay, say that one more time. You give me any little interval around 0, and as long as 1 over n is inside there, then 1 over n times the sine of n is going to be inside there, because sine of n just gives you something between 1 and -1. So as if you want to make this little interval smaller and smaller, you can, and you just choose n larger and larger, and so that those values are going to get closer and closer to 0 and stay close to 0. So there's that one. Here's another one. ln of n over n. Okay, both of those things are getting large, right? The ln of n gets large and n gets large. And so if we were to graph that, one way of thinking of graphing that, if we go back to the whole x-axis, if we have the ln of x, f of x, is equal to the ln of x over x, whatever this function looks like, it's going to eventually look something like that. Then ln of n over n is just going to be points along that function. And so what all we really need to do is find what's the limit of the ln of x over x as x goes to infinity. And whatever limit this is going to be the same. And I say it's going to look like that. Can you see why? Because x grows faster than the ln of x, and so this ratio is going to get smaller and smaller. How do I know it's going to grow faster? Well, I guess the technical way of doing it is by using L'Hopital's rule. Remember that from Calc 1? If you use L'Hopital's rule, you notice that both of these things are going to infinity. And so by L'Hopital's rule, you can take the derivative of both the top and the bottom, and you're going to get 1 over x over 1. And sure enough, that limit is 0. So since by L'Hopital's rule this goes to 0, that means that this goes to 0. And since the whole function goes to 0, certainly points along that function are going to go to 0 as well. So that's kind of an important thing to realize, okay? That a lot of times you can just work on this one instead. Let's look at one of my favorites now. It's this sequence right here. It's the limit of 1 plus 1 over n to the n power as n goes to infinity. I discovered this one myself. I mean, I discovered it for myself way back when I first got a calculator. I had a calculator that had power buttons, and I started playing with it because I got curious. What if you were to take 2 and you square it versus 1 plus 1/2. No, I'm sorry. Here, let me start again. If you take 1 plus 1/2, which is 3/2, and you square it, how does that compare with 1 plus 1/3 cubed? How do those two compare? Because this is obviously a bigger number than this, but then this one you're cubing, whereas this one you square it. And how do those compare with 1 plus 1/4 to the 4th power? Or if you keep on going, 1 plus 1/10 to the 10th power. Or you keep on going, 1 plus 1/1000th to the 1000th power. What's going to happen to that? You have two things that are in tension, okay? And this is what makes limits especially interesting when you have these things called indeterminate forms, where you have two things that are fighting each other and you don't know which one wins. Okay, let's think about the fight here. What's going on inside? What's going on inside is this thing is getting closer and closer to 1. And we know that 1 to any value at all is just equal to 1. So this inside is trying to drag this thing to 1, and if it ever hit 1, 1 to any power is 1. So you might argue, well, this is really, as this gets closer and closer and closer to 1, then 1 to any power is also going to get closer and closer to 1. So one good guess is that this thing converges to 1. Be very reasonable. On the other hand, it never actually hits 1. It's always just a little bit bigger. And if you take any number just a little bit bigger than 1 and you keep multiplying it by itself, this is fixed now, a fixed number bigger than 1, and you keep multiplying it by itself over and over and over, it's going to go to infinity. Because you take a number greater than 1, you keep multiplying it by itself over and over and over, it's going to go off to infinity. So, possibly that's what's happening. You could argue, oh, this thing never hits 1. It's just always a little bit bigger, and you take any fixed number bigger than 1 and you keep multiplying it by itself over and over, it's going to go off to infinity. Well, of course, neither of those arguments totally works. If this actually hit 1, then this would be 1. If this were a fixed number, and then you took it to a larger and larger power, it would go to infinity. Neither of those works. They're both just arguments to try to guess at what the answer might be. So maybe the answer is 1, maybe it's infinity, maybe it goes to something in between. Okay? So let's try to figure it out. It's a wonderful problem, one of my favorites in all of mathematics. So the first thing we're going to do is we're going to say, okay, this is true of n, so it's also true of x's. So this is going to be equal to the limit of 1 plus 1 over x to the x power as x goes to infinity, as I had mentioned in the previous problem. Okay, so we'll look at it for all x's. Now, I also remember this. I'm going to get rid of this now for the sake of space. And I'm going to remind myself that a to the x is equal to e to the ln of a to the x, right? Because they undo each other. And that's equal to, you can bring the x down, e to the x ln of a. So whenever you have something of the form a to the x, you can always write it as e to the x times the ln of this a. So this thing right here, I can write as the limit as x goes to infinity of e to the x ln of 1 plus 1 over x. Okay, so I can do that. I haven't changed anything. And finally, since the exponential is a continuous function, if you remember what a continuous function, what property it has, the definition of a continuous function is that the limit as x approaches a of f of x is equal to f of a, and most books, authors don't write it like this in their book, but I wish they did. I wish they'd write it like this, is equal to f of the limit of x as x approaches a. That would be a fancy way of writing a. A is equal to the limit of x as x approaches a. And the reason I like that is because what it tells you is that if you have a continuous function, you can bring the limit inside the function and things will stay the same. And since this is a continuous function, I can do the same thing here. I can write it as e to the limit as x goes to infinity of x ln of 1 plus 1 over x. Okay, a less rigorous way of saying it is all the actions happening up here. So as x goes to infinity, e just stays e, and this is where the action is. So the point is, that's what we're after now. Okay, so how do we find that limit? Notice that this is another indeterminate form, because now you have something else where two things are fighting. As x goes to infinity, 1 over x goes to 0, which makes this thing go to 1. and the ln of 1, is equal to 0, right? So that means that this whole thing here is approaching 0 as x gets big. On the other hand, this thing's going to infinity as x gets big. So you have those two things that are fighting. What happens when you have one thing that approaches 0, it never actually hits it, it just approaches it, while this thing approaches infinity. It gets larger and larger. They're fighting. Which one wins? Same thing as before. Maybe this one will win. Maybe the answer is 0. Maybe this one will win. Maybe the answer is infinity. Maybe it'll go to something in between. Let's see once what happens. So here's our function now, or here's the problem now. We want to take this limit and the question is, how do we go about solving it? And the answer, in case you've forgotten, this is something, again, I do in Calc 1, is I say, okay, this is a place where you can use L'Hopital's rule. It's a disguised place where you can use L'Hopital's rule. Remember L'Hopital's rule, you need something of the form 0 over 0 or infinity over infinity. Okay, plus or minus, it doesn't matter. This is of neither of those forms, but we can put it in that form. Look at here. I can write this as the ln of 1 plus 1 over x, all divided by 1 over x. Agreed? Just a little algebraic trick. I can write it like this. And now, as x goes to infinity, both of these things are approaching 0. See that? So now we can use L'Hopital's rule. I always like to put a little L over that to indicate I'm using L'Hopital's rule here now. And L'Hopital's rule, as we just mentioned a minute ago, says that you take the derivative of the top, and this is, notice why I need the x in here. It doesn't make sense to take the derivative of a sequence. If you have a bunch of points like that, there's no derivative of it. You need, if you're talking about the slope of a function, you need a differentiable function there. So that's the reason for having changed it to x's. So here we go. So I take the derivative of the top. The derivative of the ln of anything is 1 over that thing, times the derivative of the inside. The derivative of the inside is this, all divided by the derivative of the bottom, which is this. And now notice, things work out rather nicely. This whole thing cancels exactly with that. And as x goes to infinity, this goes to 0, so I get 1 over 1. So it turns out that this goes to neither infinity or 0. It compromises and goes to 1. And more importantly, it means that our answer over here is going to be e to the 1, which is e. Which means that this thing right here doesn't go to either 1 or infinity, it goes to e. It finds a compromise between the two. So go ahead and try that on your calculator. Take 1 plus 1/10 all to the 10th power, or 1 plus 1,000th to the 1,000th power, and you're going to get something pretty close to e, which is what, 2.71, something like that. So there you go. Very nice problem. Let's do another one. What's the limit of a to the n as n goes to infinity? Well, if a is anything larger than 1 in size, then notice that you take anything larger than 1 in size, it's going to just keep getting bigger and bigger and bigger as you multiply it by itself over and over and over again. So this limit is going to be, let's just say that it diverges if a is greater than or equal to 1 in size, greater than 1. Okay, take 2 squared, 2 cubed, whatever, it's going to keep getting bigger and bigger. If it were 1.1, same thing. Negative, it's going to be the same sort of thing, it's just it's going to alternate in sign. Okay, so that's true. What happens if a is equal to 1? If a is equal to 1, then then let's put a whole bunch of answers here. This let's just say it. Let's put the equal out here. Kind of abuse it, and let's say diverges if A is greater than 1 in size. If A is equal to 1, then it's going to be 1 to any power is equal to 1. So the answer is going to be 1 if A is equal to 1. If A is equal to -1, then what do you get? -1 to the first power, -1 squared, -1 cubed, -1 to the fourth. What happens to all these? That's -1, that's +1, that's -1, that's +1. It's going to keep alternating between 1 and -1, which means the sequence doesn't converge. It just keeps bouncing back and forth. So I'm going to say it diverges if A is equal to -1. And finally, what happens if the size of A is less than 1? What happens then? So what happens if A is less than 1 in size? You could probably guess at the answer because we're taking something smaller than 1 and you keep multiplying it by itself over and over again. It seems like it has no choice but to just kind of keep going down towards 0. But let's prove it, okay? Here's the difference between a good guess and a proof. Let's prove it. So let's first start off by assuming that A is greater than 0. Okay, so A is greater than 0 and it's going to be less than 1. So given that, do you agree that A sub n is always going to be greater than or equal to 0? I guess we can take it to be greater than or equal to. Do you agree that A sub n is going to be greater than or equal to 0? You take any positive number to a power and it's still going to be positive. So that's going to be true. Check. Agreed? Here's the other thing to notice. So in particular, 0 is a lower, I'll call it a lower bound. Okay? It's bounded below. It's bounded below by 0. This sequence is going to be bounded below by 0. Then here's the other thing I'm noticing. I'm noticing that A to the n plus 1, which is the next term in the sequence, is equal to A times A sub n. But since A is less than 1 in size, that means that that's less than A sub n. Agreed? Because this thing is less than 1 in size, and so this is strictly less than this. So that tells us that the sequence A sub n is monotonically decreasing. Okay? It's decreasing. So now we know that this function is both bounded below by 0 and it's also decreasing. So by the theorem that we had yesterday, or in the previous lesson, we know that this thing is going to converge. It has no choice to converge. So I can just say, the limit of A sub n as n goes to infinity, it exists. It's equal to L. We don't know yet that L is equal to 0, but we know it converges to L. So now we have to prove that L is equal to 0. So watch how you can do this. Here's the first thing you say. You say, well, okay, suppose that limit is equal to L. Then the limit of A times A sub n is going to be equal to, this is a constant times the sequence, so that's going to be equal to A times the limit, which is the way limits all behave, whether you're talking about limits of sequences or limits of functions. If a limit exists, goes to L, then a constant times that limit is going to, times that sequence is going to go to that constant times the limit. So that's true. But notice that this thing is just equal to A to the n plus 1. So this right here is the limit of A to the n plus 1 as n goes to infinity. And this is just the same sequence as this, is just one farther away. If you have the sequence 1, 1/2, 1/3, 1/4, 1/5, 1/6, and you start here or you start there, one is marching right behind the other one. They're both heading to the same limit. It's just that one is just one back from the previous one. So this limit's also got to be the same as this one, which has got to be L. And so that tells us that A times L has got to be equal to L. So A times L has got to be equal to L. You bring the L over to the other side. AL minus L has got to be 0. And so factor the L out, and you get L times A minus 1 is equal to 0. And since A is less than 1 in size, this thing can't be 0. And since this thing can't be 0, and the product is 0, that means that L's got to be 0. So there's the proof, okay? Kind of clever. A very clever proof. I doubt if I would have come up with this myself. I just remember reading it in a book. So there's the proof that if A is between 0 and 1 in size, then the limit is actually 0. And now, if you let A be a negative number, if you think about it, okay? So if A is a positive number, this limit is going to be 0. And so now if A is a negative number less than 1 in size, then the only thing that's different is that some of these things will be negative rather than positive. But they're all marching into 0, either from the left or from the right. They're marching into 0. And so we can finally say that limit is 0 if the size of A is less than 1. So that's kind of, we're going to be using that. We're going to be using that result in the next section. It's a rather important result that we're going to be using. So that's why I wanted to spend a little bit of time on it. Okay, so that's that one. Let's see, are there any others to do? There's some interesting ones. Let's look at this is one of my favorites. Again, you can do this with x's just as well, and I do it with x's back in Calc 1, but you can do it this way as well. What happens to that limit is n goes to infinity, and I love this one again. It's again one of my favorites because you can't figure out what the answer is going to be. You can't tell just by looking at it. It eludes just casual thinking. Here's one way of thinking about it. One way is you say, well, this n is insignificant compared to the n squared. Okay, the n squared is much more important than this. So if you just get rid of this, then you have the square root of n squared is n minus n is 0. So it might be that as n gets big, since this thing is insignificant compared to that, maybe it kind of just fades away and you get n minus n is 0. So that's a reasonable answer. That's certainly the kind of logic to use if you have something like this. And you take the limit of that as n goes to infinity. You say, oh, this thing is insignificant compared to this. This, it doesn't matter what that is insignificant compared to this. You can divide both the top and the bottom by the highest power of n on the bottom. And when you do that, I'm just doing another problem here right in front of you. How do you like this? You're going to end up with 1 plus 10 over n, all divided by 3 plus 100 over n squared. And now those two things both go to 0 as n gets big, and you're going to get 1/3. So my point is that in a situation like this n is insignificant. The n squareds are the only thing that matter, and so the answer is 1/3. This is not quite so easy to make that argument because you're not dividing by a power of n that's going to just kind of annihilate that the way you do here. And yet, it still seems to be the case that it's kind of insignificant compared to that. Another person could argue, wait a second, this thing right here is 0, but you always keep having that square root of n, and as n gets big, just that contribution itself maybe makes it go off to infinity. So I could believe both of those answers. If I didn't know the answer, I could be made to believe both of them, and that's what makes it a lot of fun. And so the question is, what do you do here? Well, let's do it kind of the way I did that previous problem. Let's try to divide it by a power of n. Well, of course, you can't change the function. I can't change the function. This is what I'm left with. But what I can do is to multiply it by a fancy form of 1. And maybe you've heard about it. It's called the conjugate. Whenever you have square roots, things like this, it's not guaranteed to work, but quite often it does work to take this whole thing and to multiply it by this. Notice I haven't changed it at all because this is just a fancy form of 1. So there it is. So now I go ahead and multiply it out. And when I do that, this times this is going to give us our n squared plus n. Then the whole reason for the conjugate is that this times this is the same thing as this times this, except that one's negative and one's positive, so they undo each other. And then you end up with minus n squared all over this denominator again. See that? So what's the advantage of doing that? Well, watch. Now these n squareds go away. See that? They cancel out, add out. And now I can do the same thing as I did in that previous problem. I can divide both the top and the bottom by the highest power of n on the bottom. The highest power of n on the bottom is the square root of n squared, which is n. There's another n. So I divide by that, and watch what happens. Take the limit. As n goes to infinity, you get a 1 on top. This whole thing is being multiplied by 1 over n. 1 over n times n is equal to 1. And when I bring the 1 over n inside the radical, it comes in as a 1 over n squared. Agreed? Because when you bring it inside the radical, you have to square it in order to keep it the same. So it comes in as 1 over n squared. You have n squared over n squared, which is 1. And then you have n over n squared, which is 1 over n. And so now we're finally done. As n goes to infinity, this goes to 0. You get 1 over 1 plus 1 is 1/2. Really cool. Not at all what I would have ever guessed at. I don't think anyone could. Okay, but go ahead and put a big number into your calculator there and check it out, and you'll see that it gets close to 1/2. So very nice problem. Okay, so again, that's another reason for kind of I just enjoy sequences. Let's do just one more, which is a favorite. Let's do the limit of the nth root of n. Again, notice this is just another example of tension. Okay, I'm giving you a bunch of examples of these indeterminate forms where you have two things that are fighting each other. Why are they fighting? This n, as this grows, it's trying to make this thing grow big, right? You take the square root of a bigger number and it's going to be a bigger number. So that's trying to make it big. On the other hand, as you take bigger and bigger roots of things, that tends to pull it down to size, right? The fifth root of 100 is smaller than the square root of 100. Right? As you take bigger and bigger roots, it becomes smaller and smaller. Okay? Sure. So yeah, very good. Okay, you got the idea. So the question is, what's going to happen there? Is one of them going to win out or not? What happens? This thing would make it want to go to infinity. If you take enough powers of something, you'd think it would pull it down to 1. So does it go to infinity? Does it go to 1 as you take more and more roots of it? Or does it compromise? Okay, which one happens? Which one works? Well, heck, let's do this. Here we go. First thing let's do is let's write it as n to the 1 over n. I can do that. And then I can write this as the limit as n goes to infinity. Remember what I told you earlier? I can write this as e to the 1 over n times the ln of n. So I've got that. Now I can bring the limit up on top and write it as e to the limit as n goes to infinity. I'll write it as the ln of n over n. And come to think of it, I guess this is one we already did, right? This is one where we changed it to x's now, and we use L'Hopital's rule. And when we use L'Hopital's rule, that went to 0. So I won't do it again. That's just going to be e to the, well, heck, as long as I said it, I'll just say it here. I'm going to first of all change it to x's. ln of x over x, and then e to the limit as x goes to infinity, and here I'm using L'Hopital's rule. It's going to be 1 over x all divided by 1, which is e to the 0, which is 1. So that thing actually does go to 1. This thing wins out in this case, okay? It wins out. Okay, I think that's it. I'll just give you one other problem to do on your own if you want. I of course just did this one. This one went to e. Why don't you generalize it a little bit? Generalize it and make it something like this. 1 plus b over n all to the c times n. And see once what that converges to. It better converge to something which resorts to e when b and c are both 1. And so you find, in fact, I'll tell you what the answer is. I think it goes to e to the bc. So if b and c are both 1, then it's e to the 1. You can check that one out on your own. Similar to the other one I did, just a little more algebra, but not bad. Okay, very good. So in the next lesson, we now, well, I guess I won't go ahead. We're going to get into the other S word. These two were sequences. Now we're going to get into the S word, which is series, coming up.